Next, we deal with the shear length of the member. Based on the shear force diagram, for beam B1 to 2, the maximum shear load is 147.6 kN. This shall be used to design the shear length. These are the equations used to design for the shear reinforcement of a beam. First, we need to determine the shear angle. Theoretically, the shear angle should fall between 22 degrees to 45 degrees. The shear resistance at different shear angle varied slightly. That gives you two equations here. We use the first equation here, which is the shear angle 22 degrees, to find the shear resistance. The FCK is given, which is 30 Newton per mm square. The BD represents the beam size. From the structural key plan, the beam has a width of 200 mm. As for the effective depth, we have calculated it while we are designing for the moment resistance. It is obtained by minusing the height of the beam with the concrete cover, the shear length, and half of the bar size. The beam height is 450, concrete cover 30, shear length 8 mm, and bar size is 20 mm. Substitute those values into the equations. We get 263.2 kN. The shear resistance at 22 degrees, which is 263.2 kN, is greater than the shear load 147.6 kN. That means the shear angle it will be less than 22 degrees. Since the principle here, when the shear angle is less than 22 degrees, we will assume that the shear angle is 22 degrees. In another word, this equation is used to determine whether the shear angle is less than 22 degrees or more than 22 degrees. If the VED, which is the shear load, is less than the shear resistance, we will just use the shear angles equals to 22 degrees in the following calculations. In the case that the shear load is more than the resistance given by the equation, that means the shear angle it will be at least 22 degrees. Then you will need to test the shear resistance for 45 degrees. Now, if the shear load is less than the resistance for 45 degrees, that means you can conclude that the shear angle will fall between 22 to 45. In this case, you will need to find the exact shear angle. This can be done by using this equation. Once you obtain the real shear angle, you're going to apply this in the following equations. In the case that the shear resistance for the 45 degrees is less than the shear load, that means the proposed beam sections is insufficient to carry the shear load. In this case, the sections needs to be redesigned. Coming back to this question, you use the equations for VRD max 22 degrees to get the shear resistance at 22 degrees, and it is found that the resistance is larger than the shear load. And you know that the angle it would be less than 22 degrees. With that, we're going to use the angles equals to 22 degrees for the following calculations. Your next step now is to determine the required shear length. Use these equations to design for the shear length, and then make sure the proposed shear length per spacing shall be greater than the minimum shear length. That means we're going to use these two equations. You know the VED, which is obtained from the shear force diagram, 147.6. D is the effective depth. We have calculated it earlier on, equals to 402 mm. Fyk is the specified yield strength. Based on the questions, the Fyk is equals to 500 Newton per mm square. As for the data, that will be the shear angle. In this case, we're going to use the shear angle equals to 22. With that, you will get the AS per S equals to 0.761. Refers to the tables of the shear length. The question states the shear length bar size is R8. Therefore, you are looking at the bar size of 8 mm diameter. The required shear length is equals to 0.761. You will need to provide the shear lengths greater than that value. The closest one, it will be this, which is R8 spacing by 125. That gives you 0.804. That gives you R8 spacing 125 mm with the provided shear length 0.804, which is larger than the required of 0.761. In the case that this table is not given in the final exam, don't panic. You can still compute the AS per S ratio by yourself. This ASW means that the area of the shear length. As for the S here, represent the spacing. It is basically a ratio of the area of the shear length divided by its spacing. Now, how do you calculate the area of the shear length? You will assume the shear length is circular in shapes. I mean the cross sections of the rebar. Then the area of a circle, it will be the pi r square. Simple formula. Now you need to remember, normally shear lengths come in a loop. When you calculate the area of the shear length, each shear length will have two cross-sectional area. Therefore, you need to determine the pi r square times 2 cross-sectional area and then divided by the intended shear length. When the size of the shear length is decided, that means the area of the shear length is constant. Now you may use your calculator to test with different spacing. You may adjust the spacing at the intervals of 25 mm, as 25 mm represent 1 inch. In industry, the workers normally work with inches instead of SI unit. Therefore, when you decide the shear length, I mean for the spacing, you can adjust the spacing by the interval of 25. For example, 100 mm, 125, 150, 175, and so on so forth. Test the ratio with different spacing until you find a spacing with the ratio slightly greater than the required. You can still get the R8 125. Once you have concluded the amount of shear reinforcements to be provided, your next step it will be testing the minimum shear length. Use these equations. FCK equals to 30, FYK equals to 500, and the beam width equals to 200. That gives you the ratio for the minimum shear length of 0.351. Refers to the table, find a appropriate spacing slightly larger than the required of 0.351, which in this case 0.366 is slightly larger than the required. That means you can provide R8 spacing at 275 mm as the minimum shear length. With that, your minimum shear length it will be R at 275. Next, you will need to compare your minimum shear length with the required shear length. There are several potential outcomes. If the required shear length is less than the minimum shear length, you're going to provide the minimum shear length throughout. The minimum shear length will set the lower limits that the minimum amount of shear length to be provided. Now, in the case that the required shear length is more than the minimum shear length, then you have to provide the required shear length accordingly. You have two options. You can provide the required shear length throughout, but you know that that won't be economical enough. Why is it so? This can be seen from the shear force diagram. For a typical beam, the maximum shear normally happens at the end of the beam, towards the midspan. The shear load reduces. When you design a beam for the shear resistance based on the maximum shear load, and you choose to apply the shear length throughout the beam, of course the entire beam will pass in shear. Just that at the middle part of the beam, you do not really require that much shear reinforcement, since the shear load is relatively small. What you can do in order to save the cost, knowing that the minimum shear length applies, whatever shear loads less than the shear resistance provided by the minimum shear length will be used with the minimum shear length. The rest, you will use the maximum shear length to be provided throughout. That will lead to a situation that you have closer spacing of the shear length near to the support and larger spacing of the shear length at the midspan. You can save some of the shear lengths here. The beam will not fail in shear even though you provide less shear length here. This is provided that the amount of shear length provided here is more than the minimum shear length. Let's say now you intend to provide the minimum shear length at the midspan where there are low shear load. You will need to determine when you need to provide those minimum shear length. First, you need to decide the amount of reinforcement bar provided as the minimum shear length, which we have already calculated just now, equals to R8 275. The AS per S ratio, it will be 0.366. We use these equations for us to determine the shear loads given by the respective amount of shear reinforcement. This ASW per S, it will be taken as 0.366, which is the minimum shear length that you have provided. The D is the effective depth 402, FYK 500, and the angle is 22 degrees. That gives you 68.1 kilonewton. Now, if you refer back to the shear force diagram here, you can draw two lines of 68.1 kilonewton. So whatever fall within the range of the 68, here you can provide the minimum shear length. Beyond that, this part and this part it will be the normal shear link. Now the question here is, how do you determine the location? You can do some simple interpolations to find when it reached to the point of 68.1 and when it reached to the point of 68.1, and this will be the range for the minimum shear link.